guys. Let me try to catch up with you a little bit. So if you're using left endpoints, the first thing I do is I really quick mark off where all the bases of my rectangles are, right, using the width that I figured out. Now, I was saying to somebody earlier, if you're doing left endpoints, you're not going to use him, because the last rectangle will stop there, right? There's no other rectangle behind it. And if you're, man, my pointers. And if you're using right endpoints, you're not going to use the first two for the same reason. Yeah.
So for the corners of the rectangles, it's not actually where the curve is, it's actually the y values?
Yeah, exactly. And that's where the curve is. The output is where the curve is, and that's why the curve is where it is. I mean, to draw, I'm not sure, maybe I don't understand the question. So the one's output is there, so that's why that first rectangle is that tall. Cool.
You're putting the x.
I was just erasing something.
That's all right. And then 1.5 is that tall, so that's why that rectangle is there.
No.
Oh, no.
Fantastic. You know how you can stick your
Oh,
tables.
there it is. I figured I was just trying to figure out how to shade it.
How to shape, yeah, okay.
So let me show you something else that's kind of cool when you have to do something like this by hand. Wow. I don't know if this has come up yet in this class, and that's one reason why I want to do this. If you've got to find several values of a function quickly. So my function is negative squared plus 6x minus 4. Go to table set right there above window. Exactly. And then you make the independent ask and the dependent auto. So now your independent variable, your x, you can just plug it in. So you can find things very quickly. Of course, you could also, anyway, this is the quickest way to do it. So I need the value at 1, 1.5, 2, 2.5, 3, 3.5, and later I'll need 4. Right. Evidence part. So now I've got all the values I'm going to need to use for my left endpoints and my right endpoints. All right, so those are all right there. So, switch it over. Yes. So now I've got my, oh, cool. So this first rectangle, it's going to be, in fact, let's be smart about this. I could do 1/2 times the height, which is 1, plus and so forth.
Yeah.
But we know procedurally it's easier to do this down here. 1/2 in front of 1 plus just all the heights. Yeah, 2.75 plus 4. And just be sure you stop at the right place. You should have 1, 2, 3, 4, 5, 6 heights. Because you have 6 rectangles. I mean, is this decent? I mean, if I bring the 1/2 through, I just get each of the areas of each of those rectangles I drew.
Why the first rectangle is 1? It's not 0.
It's true.
There's no height for the first rectangle?
So the height is going to be based on how far up it goes from 1. And at 1, this is negative 1 plus 6 minus 4, that's 1. Right? So the first rectangle's height, the only reason this guy's height was 0 is because the output of 0 is 0.
But now we have 7 points to plug in instead, because I consider the last point, which is 4, included.
Why would you though?
Because there is a rectangle right there, right?
But how tall is that rectangle? Is that rectangle's height based on 4?
No, based
No.
on 3.5.
Exactly. So 4 doesn't come into play.
History.
The output of 4 doesn't come into play. If you use it, you got somehow too many rectangles. You've gone too far over. Don't make that a big deal. If you use left endpoints to determine how high your rectangles go, you're not going to use that last number. It's the right side of that last rectangle. You've already used the left side of it to figure out how tall it is. So you don't need that last number. Maybe. So again, this is almost too simple of an idea. It's different. We've never really looked at something like this before. But it's relatively simple. It's almost too simple to trust. And then what do you get when you add all of that? Do all that stuff.
23.25 divided by 2,
Yeah.
11.65.
I got 11.875.
Neato.
Bunch of answers. Woohoo.
All right, so let's see. Yeah, you definitely get.
It just depends on what value you set up.
5, 18.5. Is that really 23? 14.5, 18.5. 21.25, 22.
Yeah, 22.25.
Yeah, 22.25. So yeah, 11.125. Okay, that sounds good.
The average is pretty close.
Now, anytime in the homework that you have to do left endpoint and right endpoint, please, dear guy, let me know that you understand you've already done most of the work. The only thing you have to do is to draw it. Okay, so if I make you draw it, you got to draw it. But then you start to realize the height of the second rectangle will now be the height of my first rectangle for the right endpoint, right? How tall is this? So I got to mark off. I want to go here, 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 here. So that's where my rectangles are going to live. Bob Ross Mathematics.
Oh.
A little bit. I'm sorry. Is it too soon? It's been a while. Come on. So now this rectangle is going to be this tall. It's going to be based on its right input height. So this rectangle will be this tall, so forth.
Oh, the graph.
So see, don't let drawing these be difficult. That's all you do. If it's a right endpoint, you start there and you draw back for the height. Left endpoint, you just do what it said the other way around.
You can use this if you want.
Calculation-wise,
It's better for you to get used to using this.
which one of these are you going to throw out?
The one.
Yeah, the one you're going to throw out for the right endpoint because now I'm not using one. I'm using this endpoint, this right endpoint to tell me how tall it is. So it's really just shifted over. 1/2 times this stuff plus now I got to use at 4. And at 4 it's 4. I don't know if you guys are with me on that. All right. So these are the heights of the right endpoints now. The one I'm not going to use. That was a left endpoint. I'm not going to use it. But now I'm going to add in the last right endpoint, which is 4. You guys, I'm kind of going, I don't know if I'm going too soon to this shortcut of how to do this work, but it's not very difficult work. So it's really all I've done is I'm not using the 1 now, but I am using the 4. So I'm not using the 1's output. Just coincidence, it's the 1. But I'm using the 4. Let's put it in 4.
Want to make it a really tiny rectangle for 1 with a you can't. Never mind, I'll take it back.
And to tell you honestly, I mean, we're not going to get into it, but your widths don't have to be the same. They can change. Your point that you pick doesn't have to be left, right, or midpoint. It could be any damn point, really. Because if I let my rectangles go to infinity, you don't have as much. All of a sudden, you have 0 room to play with. So let me see if I can make this make sense. Anytime n is finite, since I'm going to go to infinity, it doesn't matter what point I really pick in there, because I'm going to go to infinity, it's going to squeeze it, and there's only going to be one choice for the damn thing anyway. So who cares what that choice was here? But to make it easier on us, calculation-wise, we've made the left, right, mid. Those are our big 3. Okay. If you do want to do anything else, just freaking go all the way and do an infinite number of rectangles. Leave you alone. Right. So what do you get when you do this?
25.25 times 0.5, which is 12.625.
That's what I got. I'm sure that's what I got.
And then when you average those,
You get 11.875.
11.875.
everybody doing the calculator?
It's 12.
Yeah,
Very
it's 12.
12.
I don't have a calculator.
Off by 1.25. Or
Not even, yeah.
Tristan,
Or 0.15. It's crazy.
no count life.
Now,
I have a calculator.
compared to some of the work we've done here, that is a breeze. It should be. You just have to get used to it. It's not something you've done before, but the work involved is very simple. I've tried to show you a few shortcuts, but you got to do some of the work to make it make sense, maybe. Right?
You have to be able to work with a sigma notation.
So again?
You have to be able to work with the sigma notation. I'm kind of like really bad at that.
All right, let's focus on the sigma notation for a little bit.
Okay.
That pretty much answers your question.
Yeah.
In fact, in section 5.2, we're going to do more with it than you want to, and let's do that. Because we have to show where these things come from that we're going to use for the rest of the class. We have to show the derivation of it, and it's going to be really pretty.
Okay. I mean sarcastic.
So let's talk about just general ideas behind the sigma notation. So if I said this,
Is that an I there at the bottom, or is that
Yeah.
a T?
that's an I.
So we start at 1,
Go to 3.
we finish at 3.
I love it. So how do you calculate the value of this?
Okay,
What was our delta x?
No. So I'm just focusing on sigma notation itself and how it works. This doesn't necessarily have any connection to finding areas or anything. It's just sigma notation, just summation notation.
Sum the endpoints, x value.
Yeah, so what's the first value? When I is 1, I have
1.
That's crazy. Plus, because that's really what that's the Greek letter S. That's our
4 plus.
sum. Good. So when I is 2,
4,
when I is 3, crazy. So it says sum up the value of I squared when I is 1 to 3.
Really using whole numbers for sigma?
I love it. It's so funny. Again, you freak me out sometimes. I'm serious. Because I was just realizing, there are situations where you might want to define your step differently. But you have to be very straight. You have to be very open about it. If you just write that, it's understood to be natural numbers. Not even just whole numbers, just natural numbers. Cool. How we doing?
So, would it look different if you were to do other than natural numbers? Would the notation itself look different?
Yes.
How would that look?
It would look freaky.
Okay, never mind.
So we're not going to go there.
Okay.
Let's see. What about this here?
Start at 11.
That's crazy.
As long as it's not 0.
Minus 2 over 11.
As long as you're not lazy, that's easy.
Yeah. So I think you start to understand the basic idea of sigma notation. Right, and this would just be plug and chug, right? This would just be 11 minus 2 11ths plus 12 minus 2 12ths plus and so forth. Up to 15. Right. So things get more interesting, of course, when you have sum I equals 1 to infinity of something. And that is so desperately not always infinity. You might think to yourself, if you sum up an infinite number of things, how the hell can that be not infinity?
Because we have an equation that when we plug in infinity would equal to 0.
So if I had
There's some of the infinite numbers.
If I had this,
Small. It's 0, roughly. It's approaching 0.
think about it. When I is 1, what do I get?
0.1.
When I is 2, 0.01. When I is 3, now keep going to infinity. What do you get?
So you just get roughly 0.1.
0.1,
Repeating.
1, 1, repeating, which is 1/9. So this is a representation of 1/9. It's neat. So part of what you're doing is actually figuring out different representations for everyday things. And believe it or not, there's a list, I don't remember how long, it was at least 100 long, of different representations of the number 1. Which if you insert those into certain calculations you're doing, it makes the calculation so much easier. Because you can multiply any damn thing you want to by 1, and then you replace that with notation that means 1, and then that simplifies what you're doing. And you're like, that is some freaky shit. That is some really cool stuff. So there's a representation for one night, if that ever helps you. Oh, you're like, man, could have used that yesterday. That's kind of neat. All right, so now tying this into what we're doing right now. Be
Surprisingly
really
straight line.
say it.
It's a surprisingly straight line.
Oh, okay, thank you. You mean for me? I understand. All right. If I write this here, screw that. I don't know why I'm making it so freaky. Jeff, don't be doing that. Freakiness. So this is delta x, right? So I'm writing it more, I'm giving it more detail than normal because I want to show you what's going on.
Wait, if delta x, it would be like your b minus a divided by
I love
n.
it. Good.
Why is it not? If one is.
I like it. It's exactly what I want to point out right now. I only deals with the number of rectangles you have. It does not directly relate to you going from something to something. So here I was going from 0 to 2, and I had 4 rectangles. That's the only reason why I had 4 pieces. I had 4. It was from 1 to 4. But I could have went from 100 to 102, and it would have been the same. It would have still been 4. I would have still went from I equals 1 to 4.
So in this case, we're just assuming that the rectangles are on the right. The right.
These have nothing to do with where you are. They only have something to do with how many rectangles you're doing, of course, right? Because what's the basic idea here? To find the area under a weird curve, I add up the areas of rectangles. So, of course, if I'm using 8 rectangles, how many additions will I do? 8 from the first rectangle to the 8th rectangle. So do I care really where I am? No. But here I was more specific. Where am I going from to? From 0 to 8.
Yes.
Right? I don't want to do. So it's something like, right? It just goes on forever. That's basically the picture. But so here's my f of x. Here's my delta x. Right? There's my sum. Yes, sir.
This is kind of off topic, but for when we're finding like the area under the curve, when we're doing that in like stats, is this related to c-scores?
Yes. Because the way I do it, in statistics we talk about, you guys are like, just stick with one subject. That's too bad. We talk about probabilities that could be like this, distributed like this. That's for that. This is the binomial, right?
Yes.
So this could be like flipping a coin 14 times. So the average number you should get is 7 heads, right? You should get 7 heads on average. So that would have the highest probability. The next highest would be 6 or 8. The next highest would be 5 or 9, so forth, right? So that's what's called a binomial probability because there's only 2 outcomes, heads or tails. Binomial. This looks very much like a very important curve, normal curve. And the whole idea of probability is it is the area under the curve from A to B. So the function that we use in statistics, that e to the negative, I think I even showed it in this class before, the x squared over sigma minus blah, blah, whatever crap.
That's for good.
Over 2 pi, blah, I can't remember the exact. You integrate this thing from something to something, find the area. But what I tell my students first is, if you just take the areas of these rectangles, that would be the probability of those things. And the area of this requires calculus, and then I tell them, that's why we have a chart. As somebody who knows calculus, actually a computer that knows calculus, spit those numbers out for us. And then we go from there. I don't teach them calculus. Thank God about that. But we could actually try to do this. I can't remember that. So that's a very quick question. I don't want to spend a lot of time on the stats. Okay. So, real quick, I haven't done one with midpoints yet, but just to show you, if I was going to do this with midpoints, because there are some in the homework that you have to use midpoints. So I still want my rectangle, the rectangles have to go, start at 1, and then go, my width is a half still. So they have to go from 1 and go by half. That has nothing to do with right or left or whatever. But now my height is going to depend on what the value of the midpoint is. You see that? That one rectangle, the midpoint, so the midpoint here tells me how tall this next rectangle is. So forth, right? So this would be basically, if I do the sum, I equals 1 to 6, f of x delta x. This would be 1/2 times, and then I just have to figure out what f of 1.25 is plus, do you guys see where that 1.25 is coming from?
Yeah.
That's the midpoint between 1 and 1.5. So the height would be determined by the midpoint of the base, right? From in this case, from 1 to 1.5.
Is the answer you get from that any different than the average of the left and right?
It could be, depending. And this is not. I didn't go all the way so it was symmetric.
Yeah.
Right? If I would have went all the way to so it was symmetric, they would have agreed. In fact, if I would have made it symmetric, the left and right would have agreed, because the over and undershoot would have averaged down on both sides. Does that phrase make sense?
Because it's a squared function.
Good. So if I have a symmetric function, I'm doing an area that's self-symmetric. Doesn't matter if I use left, right, or mid. They're all going to agree. This I didn't go all the way, so the midpoint would most likely be different from the average.
Okay.
But I would put money on it being at least as good.
Oh yeah, like point off, a few points off.
Exactly. Yeah. See, now I cover my ass by not telling you how much money I would put on that. Could be a penny. So do you guys get the idea there?
Yes.
So they could ask you to do midpoints in the homework.
And that'd just be an M6 because you're doing 6. Right?
It's crazy. M6. I love it. Right? I'm not a fan of overuse of symbols for silly things, but oh well. That's what the book uses. No worries. Okay. So a couple of cool things comes out of this. Here we go. Where do they summarize this? Somewhere here.
Is that the one where they had like a bunch of smaller square rectangles together? Like 10 and then 100 and like 1,000.
Oh, they sort of do that already. Oh, yeah, we're already doing that. Good.
Question.
Yes.
If we do the midpoint, we don't have to do right and left, right?
Sorry?
If we do the midpoint, we don't have to take the right and the left thing here.
Only if I ask you to.
Because it will give us the same answer, right? If we calculate the midpoint immediately right like this, it will give us the answer 11.875.
And it completely depends on the function you're looking at. So we are looking at really well-behaved functions. So you have to imagine that there could be places where it depends on the luck of the draw when you have some really funky function going up and down like crazy. Does that make sense? Okay. So I think the last thing I want to do, this is going to take a little while, that's why I don't get too excited, is talk about the next level. And of course the next level would involve actually taking the limit. The limit as n goes to infinity. It's a good thing you're here. So let's take problem out of the homework here. And actually, we need a couple of things first. Here we go. Perfect. This is what I was looking for. Let's see how much time we got. I don't know if you guys have ever seen this before, but I always teach this in my Math 120 class. Math 120 I call the fall through the cracks math. It's math that could be taught in other courses but never is. So this thing, very simple looking idea, right? I mean, how would you represent, start it off saying it's something big, the first few would look like, how would you start this thing?
2 plus
Yeah,
3
yeah,
plus
exactly.
4 plus 5
Sounds like,
plus
what the
10.
hell you want me to say? plus n. Kick ass. So you could actually figure out a representation based on n, a closed form, something called a closed form for this. It's not like a bunch of sums, right? I'm actually using closed form incorrectly, then I don't care. You can find something that's just a function of n that doesn't have all these terms in it, and it's something. It's a urban legend from, believe it or not, from mathematics about Gauss. So if you don't know Gauss, that sucks, because Gauss is the guy behind the normal curve, for example. Gauss did way too much stuff. Gauss's law in physics, kick ass. So we could have a whole semester of Gauss, but we're just going to do a little bit. The urban legend was class was driving the teachers crazy. It's like a grammar school class, little kids. And the teacher said, everybody sit down and add number 1 through 100. So I have no idea where he's from.